Good evening. My name is Betty Karemi, bed 050067/2021, specialized in mathematics and business. And today I want us to learn more about real analysis. Let's get to see more on review of real numbers, sequences, and continuity. And we will specify more on real numbers for today. A system of real numbers R may be constructed out of the system of a rational numbers Q, and we take this construction as known. The formal definition is that a real number is a cut of rational numbers. For example, a subset of a rational number that is neither Q nor the empty set has no largest element and contains all rational numbers less than any rational that it contains. The idea of construction is as follows. Each rational number Q determines a cut of Q star, namely the set of all rational numbers less than Q under the identification of Q with a subset of R. The cut defining a real number consists of all rational numbers less than a given real number. Write the set of cuts gets a natural ordering given by inclusion. In place of great or less or equal to, we write a slanting V and a dash. For any two cuts R and S, we have R less or equal to S, or S equal less or equal to R. And if both occur, then R is equal to S. We can then define less, greater or equal to, and greater than in and in the expected way. The positive cuts are those with 0 star, less R, and the negative cuts are those with R less than 0 negative, 0 star, I mean. Once cuts and their ordering are in place, one can go about defining the usual operations of arithmetic and proving that R with these operations satisfies the familiarity, associative, commutative, and distributive laws, and that these interact with inequalities in the usual ways. The definition of addition and subtraction are easy. The sum or difference of two cuts is simply the set of sum or differences of the rational from the respective cuts. For multiplication and reciprocals, one has to take size into account. For example, the product of two positive cuts consists of all product of positive rationals from the two cuts, as well as 0 and all negative rationals. After this definition and the proofs of the usual arithmetic operations are complete, it is customary to write 0 and 1 in place of 0 star and 1 star. An upper bound for an empty subset E of R in a real number M such that X less or equal to M for all X in E. If then an empty set E as an upper bound, we can take that cuts that E consists of and form their union. This turns out to be cut. It is the upper bound for E, and it is less or equal to all upper bounds for E. We can summarize this result as a theorem. Theorem 1.1, in an empty subset E of a real number with the upper bound as a least upper bound. The least upper bound is necessarily unique, and the notation for it is SUPX, supremum X element EX. Yes. Or sup X, X element E. Sup being an abbreviation for the Latin word supremum, the large, or the supremum in short means the largest. Of course, the least upper bound for a set E with an upper bound need to be in E. For example, the supremum of the negative rational is 0, which is not a negative. For allowable for an empty set E of R is a real number M such that x less or equal to, or x greater or equal to M for all x element of E. If M is a lower bound for E, then negative M is an upper bound for the set negative E of negatives of numbers of E. Thus, negative E as an upper bound. And theorem 1.1 shows that it has least upper bound supremum x elements negative E x 10. Negative x is the greatest lower bound for E. This greatest lower bound is denoted by infimum y element ey or infimum y element ey, if being an abbreviation for infimum. We can summarize as follows. The nodes are any non-empty subset E of R is lower bound as the greatest lower bound. A subset of R is said to be bounded if it has an upper bound and a lower bound. Let us introduce notation and terminology for intervals of R. First, treating the bounded one, let A and B be real numbers with A less or equal to B. Then open interval from A to B is the best. AB is equal to X, element of R. A less X less B, the closed interval is the set. AB is equal to X, element of a real number. A less or equal to X less or equal to B. And the half open intervals are the best. The set AB is equal to X, element of a real number. A less or equal to X less than B, and AB is equal to X, element of a real number. A less than X and less or equal to B. Lower bound and each of the above intervals is indeed bounded. Having A as a lower bound and B as an upper bound, these intervals are non-empty when A is less than B or when the interval is AB with A being equal to B. And in this case, the least upper bound is B and the greatest lower bound is A. Open sets in R are defined to be arbitrary unions of open bounded intervals, and a closed set is any set whose complement is R is open. A set E is open if and only if for each X element of E there is an open interval AB such that X element AB has or equal to E. In this case, we of course have A less X less B. If we put greater or less 2 is equals to mean X minus A or B minus X, then we see that X lies in the subset X minus element X plus element of AB. The open interval X minus element or X plus element equals to Y element of a real number Y minus X less than E. Thus an open set is an Y set E such that for each X element of E there is a number less or equal to or greater than 0 such that Y element of a real number Y minus X less E lies in E. Thank you very much for your cooperation. Thanks for attending the class. Let's meet in our next class. Have a nice evening.